Hey guys, it's Mr. Wolfe here, and I'm going to be going over the second part of Target 1, focusing on net force. So if you guys, this is your guys' target sheet right here. If we look at the target, we're going to just look at this portion of Target 1. I can analyze situations where the net force is going to be 0 and determine the individual forces acting on an object. That's all we're going to be looking at for this target sheet right here. And we're going to be incorporating these ideas that we looked into the last video. All right, so a good way to understand the idea of net force is to look at the question, when will an object be in constant motion or when will it be in changing motion? So let's look into these a little bit more. So constant motion is when our object is going to be moving at let's say, a constant speed. It could also be at rest. Right? And really at rest is a constant speed. Let's say I have a cup right here and we check in at time 0. It's at 0. It's traveling at 0 meters per second. Let's check back in 5 more seconds. It's still traveling at 0 meters per second. So even though it's not moving, that's still a constant speed right there. So we could say that it's at rest. All right, our other one is going to be, instead of constant motion, changing motion. And so when our object's in changing motion, it's either going to be increasing or decreasing speed. Or it could also be changing direction. And so in order to determine whether our object is in constant motion or changing motion, involves forces. And so what is a force? Simply put, a force is a push or pull on an object. Right? A force is needed to change an object's state of motion. All right, so in order to have changing motion, we have to have a force. And then finally, a force is not required to keep an object in motion. All right, so that's the idea behind force, but as we know from everyday experience, if we have an object, let's say this is our object, it could experience not just one, but multiple forces. So maybe this object isn't experiencing a force going this way, maybe another force with less magnitude going this way. You could even have forces going up and down. So when it comes to determining how this object is going to move, that's when we're going to be looking at our net force. And our net force is essentially going to tell us how the object moves. And what our net force really is we just take all these individual forces acting on the object and add them together. So it's the combination of all forces acting on an object. And so a mathematical way of representing this is our net force is equal to just all the forces adding up. And they could continue if we have more forces present in our particular situation. All right, so an important thing to also recognize with net force is that it's going to depend on the magnitude and direction of individual forces. All right, so let's say we add up all our forces. How is that net force going to tell us about the motion of the object? Well, anytime our net force is greater than 0, we're going to have changing motion. And anytime our net force is equal to 0, our object is going to be in constant motion. And keep in mind for this target, what we're going to be focusing is I could analyze situations where the net force is going to be 0. So let's look at some examples in which our net force is going to be 0. So let's look at our first problem right here. A kid applies a force of 400 newtons to a fridge. And so I'm going to draw my fridge right here. Here's the floor. and he's applying a force of 400 newtons. Now I could have drawn this force in the other way, but since I'm drawing it to the right, I have to draw that it's positive 400 newtons to the right. But we know that our fridge won't budge, and this is a huge key right here to keep in mind. It's telling us what the motion of our fridge is, and that's essentially that it's at rest. And so we know that when an object is at rest, the net force is going to be 0. So I'm just going to draw right off the bat, my net force is equal to 0 for my object. All right. And then what is the frictional force that is preventing the fridge from moving? So the frictional force is always going to be opposing the intended motion. I'm just drawing a dotted line because we really don't know what this frictional force is yet. But we can figure it out by using our net force equation, because our net force is going to be equal to all our forces added together. And in this case, we have the applied force minus the frictional force. And I put minus here because the frictional force is acting towards the left, in the negative direction. Right. We also know that like I said before, that our net force is going to be 0. So I'm just going to substitute net force to be 0 here. And our applied force is 400 newtons. And what we're solving for is, what is the frictional force that is preventing the fridge? So 400 minus the frictional force, we could look at this and say, all right, in order to get 0, 400 minus 400 is 0. And so my frictional force is going to be 400 newtons. But remember, this is a vector quantity. I know my frictional force is going towards the left, so it's going to be negative. So anytime you have a problem and it describes the motion of an object, whether it says it's at rest, it won't budge, or it's moving at a constant motion, you know right off the bat to write that your net force is equal to 0. So let's look at a new situation right here. Here we have a car that's moving, not at rest. So a car engine applies a force of 500 newtons. So I'm going to draw my object. Here's my car right here. Here's the ground. And it's going to apply a force of 500,000 newtons. I'm deciding to make that go to the right. So 500,000 newtons. I put the positive here because it's going towards the right. The friction of the road provides a force of 450,000 newtons. And we know from that last problem that the frictional force is going to oppose the intended motion. So it's going to be going towards the left, that opposite direction. So 450,000 newtons to the left, shown by the negative. There's also going to be a force of air resistance on our car. That's going to be negative 50,000 newtons, or 50,000 newtons to the left. Now what I also want to do is I do want to label my forces. So here's my applied force, my frictional force, and my air resistance force. I'm just going to make that FR. So what's the goal of this problem? It's to determine the net force and to describe the motion of the car. And from my net force, I can describe the motion of my car. Oh, and one thing is that your sheet is going to say that this is initially traveling at 30 miles per hour. Mine doesn't, but I'm going to write that in. My velocity initial is 30 miles per hour. All right, so I know in order to determine my net force, let's use the equation for net force. My net force is going to be equal to all of the forces added together. And so I have my applied force, and then I'm going to say minus my frictional force minus the force of air resistance. Drew these with a negative because they're moving in the negative direction. All right, so my net force is equal to, my applied force is 500,000 newtons minus, that's that negative there, 450,000 newtons minus 50,000 newtons. And if you do the math on this, you're going to see that your net force is equal to 0, and we have to have units, newtons. All right. So we know our net force, and now we have to describe the motion of the car. Well, if we look at our table from before, when our net force is 0, our object is moving in a constant motion. And specifically, we could go a little bit more in depth with that because we know that initially the car is moving at 30 miles per hour. And if it was moving at 30 miles per hour initially and it's moving at a constant speed, it's moving at a constant speed, and that constant speed is 30 miles per hour. All right, so this is the idea of net force and using it to describe the motion of an object. When our net force is 0, our object is always in constant motion. If our net force is anything but 0, our object is going to be changing its motion.